Yeah, I think now we are fine. It's recording. But now, what I simply mean is these are the questions that you should expect actually. All these same courses of question, what is changing is just the shape, but the question are the same. Look at question 5. They want you to get to normalize eigenvalues, eigenvector, and then the p matrix, just like the other one. When you come to question 6, differential equation, state space model. When you come to question 7, dynamic equation, normalize whatever, whatever, and whatever. These questions as repeat, they are repetitive. So what you need to know is simply to understand what is going on. Under this such of topic, when we have steady state, we have how many questions? One, we have two, no, one, we have two, no, not this one. We have two, and then we have three. So there is no, if we have time, we can solve the three of them. But what I want you to get is how to solve it. If you can get one or two, believe me, you will be fine with this type of question. So what we're gonna do is like tonight, we start with question 1 and we see if we finish it. If we still have time, we can take another question or not. Tomorrow we will do another type, even question 2, that has normalizing stiffness, natural frequency, eigenvalues, and this one. So basically we will be answering all the possible questions that can come under this topic before we move to the next one. Yet, you see a lot of figures, you see this thing is complicated, how to go about it, but they are cheap. It's not much like cheap. So what you're gonna do without wasting time, we're gonna move on question 1. So Mabuza, what we did today, I simply explained how to normalize natural frequency, eigenvalues, and eigenvectors. The good thing is we have not solved any problem yet under yeah, under
Hello.
yes, I'm talking.
I think you were experiencing network issues. I'm not sure if whether it's my side or your
No,
side,
no,
but
I'm fine.
then
It's not
you
network.
just went quiet.
I was just reading something.
Oh, okay,
Yeah.
because you just went quiet. Okay, then you can continue.
Now, what I was saying, basically, we explained this. So we have not yet solved a problem on that. So, yeah, what we're gonna do, let's start by solving a question. Yeah, what is question 1? Did we do question 1? Wait, let me make a call, please. Yes, talk to me, Malina. Talk to me. You say that we should not redo. Yes. Ah, Mr. Kwoto. I'm okay. Send, let me see. Hey, Mr. Kwoto. Nah, I'm checking. Where is it in the group? Uh, is it the same problem? Let me see. Yes. Did we do the steady state question? Did you do the steady state? Can you please add quick recap what you did? Uh, Wait, when did we do this one? Eh, okay. No, actually, I wanted to do this because I have not done steady state with you. Yeah, I don't know, but if we said we did it, I don't know. I don't know if that would be fine. Okay, no problem, Mr. Foster. Let me just do this with them quickly. I'm saying no problem. Let me just do this quickly with them because apparently I have not done steady state yet. I don't remember when did we do steady state here. But don't worry. After the class, you can give me a call. We discuss that question two together. Okay, my brother. Okay. Okay. Yes. I don't know who's texting me. Am I the only one experiencing network issue? No, you are not. I'm here. I was, like I said, I was on the call. Guys, Mr. Bubakar, have we done this question here? You know what, guys? Let's just do this quick since. Matters. How's it, my water? Not sure. But it seems like shit. What's going on with me? What is going on with me? Okay, guys, this is question one. So I think I received the text. Can you please? I don't know who's that, but that text went down. Or can you please quickly recap what you did yesterday so to have a clue far you are? Um, I don't know how I can do a recap on that. Definitely don't know how, but literally what we did not do any calculation basically. So what we did, we went through this explanation how they got the angular
Nakina
speed.
Noresta.
You saying, Mr. Koto?
Ya Arthur. Khonoro Balawan.
Mr. Koto, your mic is on. I don't know if you're speaking to me. Yeah, we actually see how to get this vector and what just by explanation. So what I was saying is this question of eigenvectors and eigenvalues, they are under question 2 and some other questions here. So actually you did not miss much, if I can say. So what we're gonna do, we're gonna see them through our questions. We're gonna find them through our example, actually through the question given to us. We're gonna solve those problems. Because if I have to do a recap, it means I basically have to explain how they get the angular speed here, how they get the eigenvalues, how they get the eigenvectors, and that's gonna be a lot of time. And yet we still gonna have to solve it, which is basically the same thing. Yeah. So what I can just ask you as a favor is make sure you attend all the classes so that we can all be on the same page. Because during the question we're gonna solve this everything that is under this topic. Yeah. So yeah, I think that's the best we can do. So what's happening is this is your question one. They want you to find the differential equation. And the method that we use here is Lagrange's. And Lagrange's, we've got a couple of videos on my YouTube channel. So what you have here, you have a system of two masses, M1 and M2. So what is the problem saying? The problem is simply saying for question one, micromechanical filter for signal processing, it is equivalent vibratory model is shown this. The system consists of internal element M1 being driven by electrostatic comp transducer and the electrostatic comp transducer sense motion. This is just the English. And two, between the two masses is coupling spring K2, and they are saying that the masses of the geometric parameters are chosen so that M1 equal M2 and K1 equal K3, C1 equal C3, and Ft is the applied force on M1. Use Lagrange's method. This is the method that we've been using to always get differential equation. So we're gonna use this Lagrange's method to determine the differential equation of this generalized coordinate x1 and x2, and then we're gonna develop the state space model of this system here. So yes, let's do it. So how do we do Lagrange's? What is this thing? This is what we have. Take this down. This is taking my space. So Lagrange's, this thing is under, there's one or two videos of Lagrange on my YouTube, you can check it. So what we do on Lagrange is we identify the kinetic energy, the potential energy, and then the, how do we call this one? It's a damper. You have potential energy, kinetic energy, and then you have the damper. There is a way that they call it again. But it doesn't matter if we don't remember it. What matters is how to solve. So first thing to do, we identify how many masses or how many objects do we have in our system. In this case, we have two objects, which is M1 and then M2. So it means we're going to be studying the Lagranges of two different masses for M1 and M2, which is basically X1 and X2. You can see the way it is represented here, Mr. Maras. So what do? You write all the kinetic energy, Chi. Kinetic energy is equal to half. Here you have M1 X1 dot square plus half M2, this is how you write Lagrange's, X2 dot square. Remember, kinetic energy in physics, we say it is half mass velocity square. Because it is mechanical, it is mechanics or physics, we represent the velocity by x dot. But otherwise, it is the same thing. It's just a quick recap. So for those who have been attending, I believe that you're quite familiar, but if it's your first time, please pay attention and ask questions where you don't understand. You also write, okay, do we need to write it like this? I think there we got a relation under this problem. They said M1 is equal to M2. I don't know if you read the problem, there is that assumption made here. So what we can do here, we can call everything to be M since they are equal. So this function here will change. You can write it like this and like this. Only under this case because they say these masses are equal. So you also have potential U. Potential U, what is the potential energy? You have two types of potential energy. Potential due to the spring and potential due to the weight. The potential due to the weight only affects when you have a change in height. Like for instance, you have a pendulum that was here that has moved to a certain angle because from the initial position to the final position, there is a height created, you have potential energy due to the weight, which is usually mgh. Only for system that does this. By that, what do I mean? If you look at a system like this, just a quick clue, a system like this one, it will have potential due to the weight because this object is rotating. Therefore, as long as it is rotating, it means there's a difference in height. And if there's difference in height, it also means that there is potential due to weight. Also, under this case here, there you see the potential due to weight. So in this our case, our mass is linear. You can see there is no change in height of the mass. That's the reason why when we are solving, we will not have any potential due to weight. So under this circumstance, we only have potential due to the spring. So in this case, we're going to be having half for the first one here, for the first pen, half k1 x1 square plus, but now look at this spring 2 here. Spring 2 is between m1 and m2. Due to that, it has to have a change. So what is the change here? It is half k2. The change is going to be between displacement of m1 and displacement of m2. So under this case, it's going to be x1 minus x2 everything square. That's it. And then you move for the third element here. It is this spring attached to this mass, which is simply plus half k3 x. The displacement is x2. Displacement due to mass 2 x2 square. So any question, guys? This we can do it fast. It looks a bit familiar, but if it is first time joining, feel free to ask if you don't understand. You have.
Can you please hi
I'm listening. Talk to me.
yes, can you quickly just explain the potential energy again? I didn't get it.
Or this one here.
Yes.
Oh, I
The
was
U.
saying when we talk about potential energy under this topic, we have two types of potential energy. Potential energy due to an object of mass and potential due to spring. One thing is sure, you always have the potential due to spring, which is half k x square. The most important thing it is this one of the weight. This one changes. It depends of the circumstance that you have. This one only exists if that mass is vertically. This is vertical, right? Let's say the mass was here and is changing to a certain angle. Because there is a change in height from the first position to the last position, there is a presence of potential energy mgh. That's what I'm saying. Now, we look at this mass here, m1 and m2. They are not changing in height. They are linear. They are only moving like this or like this, back and forth. So under this case that we are, you cannot have any potential due to the weight. It cannot exist because your mass is on the linear motion. There is no change in height of mass. That's one of the reasons. So I don't know. Did I answer you?
The equation. I was talking about the equation. The U.
Oh,
U
the U,
half
this one
K1.
half. This one here.
Yes.
Oh, okay. Hey, Mr. Kotso. Hey, Kotso, I don't see him. Yeah. Okay, what I was saying, when you look at this, you deal with it system by system. For the first one, you can see it's one spring attached to one mass. So it's kept as that half kx1. But for the spring 2, it's not only attached to one mass, it's attached to this mass and also to this mass. Because of that, there have to be a change of displacement. So the displacement due to mass 1, which is x1, and displacement due to x2, which is to m2, which is x2. Because the spring K2 is holding two masses. So definitely, for us to get potential energy, we have to get change in displacement between the displacement of those two masses that it is holding. Now, when you do this change, you can do x2 minus x1 or x1 minus x2 is still the same thing, but preferably when I do this and when we do it here, we start from the first one minus the last one. So that's the reason here for K2, we have x1 minus x2 squared. And when we move from the spring K2 here, it's only attached to one mass, which is M2. So that's why its displacement is the one that goes with mass M2. Is it making sense?
Yes, thanks.
You're welcome. Now, I don't know, did they say anything about K? If you check again that question, I think they said K1 is equal to K3. This was the assumption that they made. They also say C1 is equal to C3. Yeah, when you read this question. Now, what is C here? C here is for the damper. Remember, X is for the springs, C is for the damper. For the damper, what do we have? We have half as well, C1. Now, what do we have here? We have X dot 1. The damper goes with the velocity. The spring goes with the displacement. So plus half, what do we have? C2 X X2 dot square. Yeah, that's basically what we have. But remember, they said C1 is equal to C3. So normally here, it's supposed to be, okay, C3 is equal to C3. But they say C1 and C3 is the same, so we can call it equal to C. So you can rewrite it nicely by simply writing everything to be C, C, and then C. That's what's happening there. So we don't have a damper here. Because of that, we only have this equation. If we had a damper in the middle here, definitely we want to have this change that we had here also with the dampers. Here we go. So what do we do? If you remember Lagrange's formulas, it says this is the formula of the Lagrange.
Hey,
Yes, Mr. Maras.
sorry. I'd like to ask something here.
No, you're not sorry. You must ask if you have
Okay,
something.
thought I'd disturb you.
No,
For
don't.
for the kinetic energy, the
Yes,
x's are the velocities.
for the kinetic energy. Okay,
Yeah.
Mr. Maras. To answer your question, remember in Math 1, if you have displacement x, right? If you differentiate
Mm.
this in terms of time, it gives you velocity.
Velocity is
If you differentiate velocity in terms of time, it gives you acceleration.
acceleration.
Yes,
Yeah.
but in physics, because this is physics or mechanics, in physics or mechanics, the velocity will represent it as x dot. The
Yeah.
acceleration will represent it as x
Will towards exactly.
dot. So the kinetic energy, because we know from physics, it is half m velocity square.
And velocity is squared.
So the velocity is being replaced by x dot only.
Okay. And then for the what's that? The potential energy is the displacement.
Is the displacement, yeah. If you guys remember, Mr. Maras, if you have the spring, the formula of the spring, it's a force, is equal to
Yeah.
k multiplied by x.
Exactly.
This is the force of the spring when you get it in physics. When we talk in terms of potential energy, it is simply half k x square. So in simple way, the potential energy goes with displacement x, the kinetic and the damper, they goes with velocities.
Okay.
The answer you
And then
understand? Yes, Malita.
Wait, for the temper, it's what? Please come again.
I said the damper also goes with the velocity.
Okay, I
Yes.
know. Thank
There's
God,
a
thank
there's
God.
a name that they call it a relay. Yeah, relay dissipation. When you heard about relay
Hmm.
dissipation under the question, they simply mean the damper. I remember the name.
Okay, no, thanks, my guy.
Sure, my leader. Yeah, let's move,
Uh,
guys. Thank you for the question, Mr. Maras. Yeah, what do we do
uh,
from here? We use the Lagranges, and guys, please, you need to know Lagranges. At least with Lagrange, if you can get the differential equation of the motion, you can at least get, can I say full mark? At least you can get 12 marks. So Lagrange says this, guys. Oh, I need to push. I need to. Guys, I'm gonna be a little bit quick. Change. I'm gonna be a little bit fast so that we can finish this question and move to something else. We have changed in terms of time, Mr. Wait, let me check that formula before I say something that is, yeah, in change of time, partial t. Now, guys, we're gonna do Lagrange for each element. For x1, this is the general formula. They say it is qi. That's my hand shaking. Qi partial t qi minus partial t over partial qi, and then we have plus partial u over partial qi. This is the formula of Lagrange. And then you have for the relay dissipation or the damper, what is this over rho qi to be equal to 0. Oh, the qi here simply stands for the variable that you're working on. We have two variables, guys. Displacement x1 and displacement x2. So we're going to do the Lagrange for each variable. So for x1, this formula will change as follows. Change in chi, partial chi. I think this one is square. It has to be square. Partial chi over partial, the variable is x1. So it's going to be x1 dot square minus, this one is always 0. I don't even know why we write it, but we write it for the sake of the formula. But it's not the master of writing it. But let's just write it. x1, the dot, wait, guys. Why am I writing this formula right? Or am I writing it? Okay. It is not square actually. It is dot here, and there's no dot on the for this one. Simply qi. So now this is what's happening. So it's gonna be partial this, partial x1 dot, okay, and then here we have partial tx1 plus partial u over partial x1. Everything should be 1 here, plus relay dissipation over partial x dot 1. Yeah, got it. So what do we do here, guys? Look at the formula how it's written, but if you're comfortable enough, if you've been attending, you should be comfortable enough when we talk about this partial derivative. This is what it means. When we say partial t, partial x dot 1, we are talking about partial derivative. Do you know what is partial derivative? You are differentiating partially the kinetic energy. So what does it mean? You scroll up, you look at the kinetic energy equation. Wherever you do not have x1 dot, it is 0. They are taken as constant. Differentiation of a constant is 0. So under this topic, we only have x1 dot for the first one here. So differentiation, Mr. Maras, when we differentiate this, it's simply going to give you mx1. Question?
Hey, you're moving too fast, eh?
I won't move so
I'm
fast.
confused here. Can
Softly.
you, yeah, can you please start from the first equation? Can you please just explain clearly?
Oh, the equation, eh? Sorry, Sisi.
Mm.
I'll go slow. Yes. Okay, this is the general formula of Lagrange. The Q here, they simply stand for the variable that we are working on. So under this our topic, we only have two variables, which is x1 and x2. So we're gonna be doing the Lagranges of both variables. First, we start with x1. So it simply means wherever you have a q under this formula here, you replace them by what? X1. Is that one fine?
Yes, you can continue.
Now, from here, we are just following now the formula. Now, this equation says equal to 0. Actually, well, let's just solve this and I will show you at the end for x1. Let's keep it the general formula like this. Now what we are doing, we are following the formula. We have partial of this in terms of time. There is something that I explained also in the beginning of this topic when we started the classes. If I have x, what is differentiation of this in terms of x? What's the answer? It is 1. Do you guys agree?
Yes, this is one.
If you have 2x, you differentiate it, you get 2.
Two
Now,
ways.
the only reason why it is like this because the variable that you are differentiating is in terms of x. Now, if you differentiate x in terms of time, x gives you the velocity x dot. If you differentiate in terms of time, x dot, it gives you x dot dot. So what is changing here? What is changing is the variable, and we have to be careful. Look at this equation. It starts by differentiation in terms of time of partial derivative. So what does it mean? It means you first get the partial derivative of this one. After you get it, you differentiate it in terms of time. Is that making any sense, guys? Babuza, is it?
Yeah, we can continue with this.
Yeah, Mr. Fathers, that Mabuza is not saying anything.
You can continue, Ice.
Okay. So now, what we are doing is we are differentiating in terms of x1 dot. So you come, look at it, said partial t. So it means you have to come to the formula of the kinetic equation. Now, what do we do for this formula here? Now, because the variable is x1 dot, so this one obvious gonna be 0 because it's partial derivative. We're only dealing with the variable when we have x dot 1. So in this case, when we differentiate this, the 2 is gonna drop, it will cancel this half. That's the reason why we have mx dot 1. This is this part that we've done. Now, the following part, we have to differentiate the answer of this in terms of time. So it means now you take derivative in terms of time of function mx dot 1. What is the answer? The answer is going to be mx1 dot dot. Why? The only reason it becomes dot dot acceleration because the variable is time. And guys, this will always be like this. It will always be like this when you will be using Lagranges. You're always gonna get the kinetic energy that you differentiate partially, and then you differentiate in terms of time to get the acceleration. That's how it is. So, any other question, guys? Yes, let's move. Let's move, guys. But please stop me too fast and ask me if you don't understand. Mr. Mars, it's fine for you, my brother.
Yeah, I'm still cool. I'm still cool, my guy. Still
Okay,
fine.
now, what happened next? We are done with this part here. You do the following one here. The following one here says partial chi, partial x1. X1. This one is 0, and it's always 0. You don't even have to worry about it. Even write it on the formula. Why is it 0, Mr. Maras? We have x dot 1, not x1. We do not have a partial of kinetic energy with x1. We have it with x dot. So this formula here, in all the cases that should be doing, it is always gonna be 0. So I do not know why they write it in the formula. It's not important. So what is necessary here? Now, what we do here, we do partial u in terms of x1. So it means we go to the potential energy, this one here. We check everywhere that we have x1. We have x1 here, so this one we can derive it. We have x1 inside here, so this one we can derive it. This one does not have x1, so definitely this one is 0. So our differential is between this one and this one. Now let's start with this one. If we differentiate this in terms of x1, do we agree that 2 will fall, 2 will cancel the half, and the only answer that you get here is k1 x1. Is it fine, guys? Differential of x squared is simply 2x. But remember, there was a half in front of it. It will cancel that half. That's one of the reasons we are only left with k1x. Is this one fine, Mabuza?
Yes, you can continue.
Okay. Now, what I want you to pay attention is this one. This one here. This one we apply what we call chain rule. You have u to the power n. So the formula says you drop the n, u prime, u, n minus 1. So how do we do? What is n? N is the power 2. Look what we have here. We have half first here. Half k2. Now let's do the differential inside here. What is n? N is 2. You drop 2. What is u prime? U prime you differentiate inside here. But remember, the variable is x1. What is differential of x1 in terms of x1? Remember, the variable is x1. So what is differentiation here? X1 will give us 1. It's going to be multiplying 1. That is the u prime. And then you copy u. U is the function the way it is, which is simply x1 minus x2. That's what we call u. Oh. x1 minus x2, everything n minus 1. Everything n minus 1, 2 minus 1, which is simply this one. So what usually happen here, 2 will cancel this. So what you have as answer, it is simply k2 multiplied by x1 minus x2. Any question about this one, guys? Let me just take the time if I have to send a new link. Any question about this one, guys?
Yeah, the chain rule. You said we start differentiating inside the bracket. Then, what did you say?
Yes, follow. Yeah. You can follow. Thank you for the question. Okay, this is the formula.
Yeah.
First of all, you need to know what is your u. Your u in this case, it is everything. x1 minus x2. Our n is 2. This one is fine, right? Mabuza, speak to me, please.
Yes,
This one is fine. Now
it's
let's
okay.
follow the formula. They said n. N is the power here. Is 2. That one is good, right? Now we want u prime. We want the differentiation of everything. What is inside here? But now, the variable is x1. Remember, it's partial in terms of x1. So it means differentiation of x2 here, it will give 0 because the variable is x1. So what is differentiation of x1? It simply gives 1. That is the reason here on u prime, we only have 1. That one is fine, right?
Yes.
And then we copy the formula that says un minus 1. So what is un minus 1? U is this function x1 minus x2. That's what I copied, x1 minus x2. So what is n minus 1? It is simply 2 minus 1, which is simply 1. Do you see it, Mahmoud?
Yes.
So now what happened? Remember there was a half in front. So the 2 cancel the half here. So this is what you are left with. So what you have here as answer,
Okay.
it is k2 x1 minus x2. So what you can do, you can even expand it. If you expand it, you're going to have k2 x1 minus k2 x2. So this is what you bring here. So we can write plus k2 x1, and then here we write minus k2 minus k2 x2. You can do it like this. So for this topic, for this problem, they actually say that, let me open again. They say that k1 is equal to k3 here. So yeah, it's actually nice. So if k1 is equal to k3, so we can simply call it k. So it doesn't change much. What I'm just trying to say is this idea we can simply call it k like this. And you can make this nicer again. Remember, you have x1 and x1 here. So you can write k plus k2 everything multiply x1 minus k2 x2. Sorry about that. So this is the potential energy for x1. This is the answer. Now yet, let me just send a new link and we consume this problem. Because we are left with 3 minutes. Let me just send a new link, guys. Mr. Toroso. Torosa. Yeah, the night will be long.
Les amis, vous vous souvenez de la fille que je vous avais raconté que super partie de la Guinée, elle est arrivée en France, elle est partie avec si on d'ailleurs, il est arrivé en France, et à un moment donné, quand sa situation politique se stabilisée, il n'avait pas son pays, il a trouvé une formation, il a demandé au pays, on peut trouver une femme, on peut trouver 5 futurs éducateurs, il a fait venir, on va poser, il a mis besoin de l'enfant. Arrivé dans les pays arabes, là-bas, quand il fallait traverser quoi,
Kazafi, we can start, right?
il a exigé peut-être là, parce qu'il y avait un autre gars, c'était réactif avec les autres, il a dit, il va pas partir de si il a été, il a accompagné une femme jusqu'à pourquoi pas.
Yes, guys, let's continue, please. If you have a question, you may ask. Let me share my screen before I forget. Yeah, okay, this is where we was or where we were. So now we have to do the same thing with also here the damper. Now we have partial damper.
Sorry, Mr. Isaac. Are you recording?
Yes, being recorded, and I will post this tonight, so you have a chance after the class to go through everything that we did. But you have to watch, because if you keep it not watching for long, it's a problem. We have partial what again? Partial x dot 1 for the damper. So it means you come on, sorry. It means you come on the equation of the damper, this one here that you see here. Because it is x1 dot, this one would be 0. It is partial derivative. We differentiate in terms of the variable given to you. So under this case, what's going to happen? The 2 will drop. So what we have here, we're simply going to have cx dot 1 for this case. Now, what do? We rewrite everything in such a way we have a differential equation for the first system. How do we do it? We simply follow this formula here. Okay, for this one, d in terms of time of this, what is the answer? This is the answer. So you start, you write, answer is mx dot 1. Now, let's move for the spring. What's the answer? But this is the answer. Now, when we write a differential equation, it's always nicer to write it in order, like x dot, x dot, and then x. So we start by writing first for the damper here. So which is plus cx dot 1. And then we write the one of the spring. So which is plus k plus k1. Let me move this a bit up for space. K plus k1 like this, everything multiplied by x1 minus k2 x2. This is it. Now equal, the formula says equal to 0, but this case it will not be equal to 0. Why? Because we have an exciting force. Usually it is equal to 0 when we don't have any presence of a force here. Because on system 1 there is a force F1G applied, an exciting force. Because of that, this system M1 will be equal to that force. But on the second system, it will be equal to 0 because there is no exciting force being applied under system 2. I hope I'm making sense, guys. Please send me the new link. Oh, hey, my brother, I forgot to there's a guy that that was here. I forgot because he have not paid yet. Can't just be efficient, this. Okay, that's what I was saying. So this case, the system 1 will be equal to f1 of t. So this is the first equation of the system using Lagrange's. Any equation, guys, and this is how we do it. We're gonna do the same thing for x2. Same thing. Let me call this equation 1. Let's do it to find equation 2. So you come again, you write the same formula is the same. Now the only difference here, you put x2, 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 x2. Otherwise it's the same. So what is the first step? You come again, you do partial t, partial x dot of 2. Now what do we do again, Mabuza? We check our kinetic. So our base is kinetic potential and relay dissipation. This is where everything comes from. Now when you look at here the kinetic energy, Mabuza, you look where you have x2 dot. It is only 1. So it means this part here will be 0. And when you differentiate, what happens? 2 will drop, 2 will cancel half. So what is the answer? Someone wants to join. Join them. Oh, Mr. Kabamba Kalundi. Mr. Kabamba, welcome, my brother. Yes. So what was I saying? Yeah. The 2 will drop, will cancel the half, but remember x1 will not exist here, x1 dot, because the variable here, people, don't cut me, I'm in a mode. So yes, this is what's happening, guys. Now, what do we do? These 2 will drop, so what will be the answer here, my boozer? Definitely here, the only answer that we're gonna have here will be mx dot 2. Same thing as this one. Now, you do now partial in terms of time of this answer. It's a repetitive. What's the answer here? Answer will be mx dot dot of 2. The reason why it is dot dot, now guys, remember the variable is time. Please pay attention on this. Do not make a confusion here. Now, what do we do again here, Mabuza? We do the same thing. We go partial u, partial x2. Now, we come up here on our equation again, Mabuza. Wait, I'm searching to repeat your name a lot. So, is it fine for review? Amfo is not here. So, what's happening here? You come to
Yes,
the
you can
potential.
continue.
Okay, if you don't have a
Yes, you
problem,
can
then
continue, but then can you clarify the part for damper, but then you can continue.
can I clarify the part of the damper?
Yeah.
On the first one here. The
No,
first.
you continue to the second one. You can clarify the second question.
Okay, the second question. Okay, no problem. Okay, under the potential that we have here, we look where we have x2. We have x2 on this one, so this one will be cut. We also have x2 under this equation. So in this case, this one will not exist. We won't be working with this one. Now, again here, we're still gonna do that chain rule for this one. Yet, let's pay attention. What do we have? We have is the same thing that we have. It is still this same equation here. I don't know if you see it. It's the same one. I can bring it aside here. It is still x1 minus x2 square. So what do? Chain rule. You drop the n, which is 2. You differentiate what is inside. But now, what is the variable? The variable is x2. So it means when you differentiate x1, it gives 0. Because x1 is not a variable of x2. Now, when you differentiate minus x2, the answer is minus 1. So you have to be careful when you do this one. Is this making sense, guys? So this is your u prime. And then you copy your u with this x1 minus x2, everything n minus 1, which is 2 minus 1. So that's what you get as answer. But remember, in front of it, you have a half k2. So this half goes with this 2. So what you basically have is this negative here. You can expand it inside. If you have to expand, what are we going to have? You're going to have minus k2 x1 minus the minus give plus k2 x1. So you can write it like this, and yeah, that's the answer that we have here. But remember, they said yes, that's what we have here. That's the answer here, Mr. Maras. So we have minus k2 x1, and then we have plus k2 x1. This is the partial derivative of this spring here. But remember, alongside with it, we have this one, which is half k3 x2 square. So when you differentiate, 2 will fall. You're gonna have k3 x2. And yet again, they said k1 is equal to k3, which is equal to k. So simply what you're gonna have is kx2 as answer when you differentiate. So this is what we have. So we can rewrite it nicely if we want. Where do we have x2s or x common x1 here? Oh, this one is x2 here.
And
Yes, Malida.
Mr. Ice.
Hmm.
Oh, yes. No, I just wanted to comment on that. You just realized it. Okay.
Thank you, Malida. So now we can create a common factor here, my brother. We can create k plus k2, everything to be x2, and then minus k2 x1. Now, Mabuza, please let's pay attention. We do for the damper, it is partial d partial x dot 2. So what do? We go to the equation of the damper, this guy here. I don't know if you see my mouse. Now we are dealing with x2, so definitely this one will be out. So our main concern is this one. So what happened? You differentiating x dot square 2. So you're gonna drop the 2. 2 will cancel 2. So the only thing that you will be left here when you differentiate, Mabosa, it is cx dot 2. That's the only thing. Because the 2, when it drops, it's gonna cancel this half in front. Is it clear, Mabosa?
Yes.
So what we have here, it is cx dot 2. Now, yet again, what do? We write this equation like for the first one. Equation 2, you copy the first answer that we got here, which is m x dot 2. Now, same order, we start with the damper, c x dot 2. What is next? You start with the spring, k2, k plus k2 to be equal to multiply by x2 minus k2 x1, everything will be equal to 0 for this one. Why is it equal to 0? Because when you look at system 2 here, there is no external force applied like on system 1. That's simply the reason. So that's it. Now, what do? Usually when we have this system, they ask us to write it in matrix form. It is always, so we have to know how to write it in matrix form. So yes, it's even here they ask determine differential equation of motion in matrix form. So we have to write it in matrix form. Let's do this. Even if it is not asked, please write it in matrix form. So how do we write in matrix form? Usually what I do, I always recall my both equation to see equation 1 and equation 2. Before I write it in matrix form, it helps me to see what I need. So I'm just gonna, I don't know if I should rewrite it or just copy it. Yeah, I can copy it, Control C, bring it here, Control V. But unfortunately, you can't copy on your test, you have to write. But on my key, on my Google here, yeah, I can do that, I can copy. I can do this, highlight everything, Control C, bring it down, Control V. Okay guys, these are the two equations that we have. Let me delete this one. So this is equation 1 and equation 2. How do you write it in matrix form? Easy as that. You write like this, your matrix. You know that under this idea, you need to get x dot dot 1, and then you need to get x dot dot 2. We do for the first one. Now, how do we do this, my Buza? The reason why I recall these two equations is not a must to recall it, but I recall it because it's like a map for me. It indicates me to see what am I going to get in the matrix. So usually what happens is I start, let's say, equation 1, equation 2. Everything that I have in equation 1 would be on top here. x1 multiply this guy here. X dot 2 multiply this one here. Please follow. X dot dot multiply this one here of 1. This multiply this one. So what actually happened? Let's delete. And yeah. Now let's start with equation 1. On equation 1, if I do x1, what do we have here? I have m, right? If I do x1 multiplied by m, I have this information here. So this one is right. Do I have any x dot dot 2 here? No. Because of that, this has to be 0. Why? Because x dot dot multiplied by 0, it is 0. It justifies that on equation 1, I do not have it. That one is fine. When I move on the second one, here, which simply means equation 2. Everything dealing with down is equation 2. Everything dealing with up is equation 1. When you move on the equation 2 here, when you do this multiplication here, guys, do you have any x dot dot 1 on equation 2? No, because you do not. This part here should be 0. In such a way that when you do x dot dot 1 multiplied by 0, it is 0. Any question, guys? Mr. Maras,
Hey, Ice.
are you with me, my brother?
Yeah, no, I'm lost a little. Please
You are
come
lost?
again.
Oh, where are you lost, my boss?
Yeah.
From where?
Not very far. These zeros, how to recount? Please come again.
From where, my brother?
These zeros, how do you come up with these zeros?
Oh, how I
When you're
come up with
saying on
these
this
zeros.
equation, you don't have x dot dot dot.
Okay,
Yeah,
yeah, I'll
please.
repeat now. I'll repeat now.
Yeah, sure.
Okay, Mr. Maras. And I believe he's not only one, so let's pay attention. Mr. Maras, I have equation 1 on top and equation 2. Is that one fine, Mr. Maras?
Yes, I'm super
Now,
fine with that. Yeah.
everything on top on this line is for equation 1. Everything down is for equation 2. How you go, Mr. Maras? I have explained this is a
Okay.
matrix. It's a multiplication. x1 multiply this one, x2 dot multiply this one, x1 dot multiply this one, x2 dot multiply this one. So basically, your x dot dot 1, it multiplies all this line here.
Mm-hmm.
Your x dot dot 2, it multiplies this line here.
Okay.
So what's happening, Mr. Maras? Whatever I write here has to make sense on what I have on my equation. When I look at equation 1, if I do this multiplication, x dot dot 1 multiplied by m, I do have it on
Yeah.
equation 1. I'm satisfied. Now, when I look at this equation 1, do I have x dot dot 2?
No.
It has to be 0. In such a way, when
Okay.
this multiply, it shows that it's not there.
Okay. Yeah, I get you.
Now, for the second one, Mr. Maras, you look at equation 2. Do you have x dot dot 1? Remember, x dot 1
No.
is multiplying. No, so it has to be 0.
Yeah. Equation 1. Yeah.
In such a way, when it multiplies, it proves that there's no x dot dot 1 there.
Okay.
Now, do we have any x dot dot? Yes. What does it multiply? They must be
Yeah.
here. So definitely m has to be here. So you are done with
Oh.
this part of masses.
Okay.
Now, Mr. Maras, we are done with that part. We move to this one. We move to one of the damper. So for the damper, we know that this side we're going to have x dot 1, x dot.
Mm-hmm. Yeah, I'm with you. Continue.
Now, what do we do, Mr. Maras? We focus on x dot 1 now. Still here. Now, here's the clue. Okay, let's do you see. We focus on x dot 1 here.
Yeah.
It's still the same thing. X1 will multiply like this. X dot to multiply like this. Same thing. Now, on x1 here, do I have a down here? We have c. Do you agree? We have x dot 1 here. It is c. In
X
such a way,
dot
when we
1
multiply,
yes.
we have this one. But we do not have x dot 2 for this one here.
Okay.
So it has to be 0. So basically, this thing is the same. On the second equation, this one is 0. This one is c.
Understand.
Is it making sense, Mr. Maras?
Yeah, it makes sense.
Now we move. This is how you write the matrix form. So please, after the class, take time to redo it. Take time. Okay, what do we have here? Now we move to the spring. So for the spring, we can do the same thing. Now for the spring, we have x1. We have what? x2. Everything will be equal to, remember, the first one has f1, the second one has 0. So what's happening here, guys? For k, what do we do? Same thing. We look at x1 here. Now let's pay attention, Mr. Mars. X1, do we have an x1 here? This one is still same thing. It multiplies here and it multiplies here. So for x1, what do we have? We have k1, k plus k1. So you have k plus k1 in such a way that when it multiplies, you have it here. Do you have any x2? You do. Do you see it, Mr. Manos?
Yeah, it's there. It's with K2.
We do have an x2 in this case, which is this one.
Yeah.
So what is x2 here? It is simply minus k2. You can see in such a way when x2 multiply this, we still find this expression here. Mabuza.
Yes. I understand. You can continue.
Okay. Now, what is happening down here, Mr. Mars? Do we have any x1? Yes, this one is minus k2. So definitely here I have to get minus k2. In such a way, when it multiplies, we have this one. Do we have any x2? Yes, it is k plus k2. So now you have written in terms of matrix form. This is what it is. But here's the clue, guys. These things, they are symmetric. Whenever you're doing the matrices, these guys moving like this, they're always the same. In all the equations that we do using Lagrange's, these guys moving like this, they are always the same. So what does it mean? It simply means that you can track your answer. It simply means that if you are not having them, this one here, they do change depending on the question, they do change. But this one, what you get here should be the same here. What you get here should be the same here. What you get here should be the same here. So this, I don't have the memo of this question, but by solving already, I know that we got this right. Why? This is the clue. So what does it mean? If you are solving this question, Mr. Maras, and you are not having this symmetric that we are seeing here, it simply means you made a mistake in one of your equations. Either you made a mistake while differentiating, somewhere there you made a mistake. So any question, guys, if you are able to do this like this, you have 11 marks.
All right, Mr. Ice, can I just ask one question?
Yes, my leader, you can ask.
Yes, on the last part there, I see that we have equal to F1 and 0. Where do we get this F1? Is it always the case that it's equivalent to a certain force, or it depends on a sketch that is given? Then another question that I had, but then I think you have just answered that. Because I remember from the class, the lecturer once said something like, you can always prove if your equation is right. But then I think with that one, I'm okay.
Oh, with this one you are okay, right?
Yes, you can just explain the F1 there.
Oh, the F1
Please.
is simply because you have the answer from the beginning. Do you see this figure? There
Okay.
is an external force
Oh,
F1 to
okay.
it.
Okay, so it's only applied at X1.
X1. Do you see this one? There is no external force.
Yes.
That's the reason why it is here. Let me show you something. Can you
Okay.
see my screen on this one, right? Do you look at do you
Yes.
see this figure here, my brother?
Yes, I've got F1 and F2. Okay.
When they derive the equation, you got F1 and F2. So to answer your
Oh,
question,
okay.
your answer is from the question. From the beginning, you know which one will be equal to the force, which one will be equal to 0. Or if both of them they equal to 0.
Okay. No. Okay, no, that makes sense. Thank you very much.
Now you are welcome, my leader. So this is it, my boss. So what else? Okay, the lecturer said already in class, the way to check if you are right, you can see this symmetric. If you are not having it, my brother, it means actually you have the map. If you're not having it, it means you can check where you are wrong. But I don't know if in the test you will have that calmness to go check, because sometimes when you go question 1, you see a mistake, you start freezing. But you don't have to freeze. Just go back and double check. Definitely you will see what is there. Any question before we do the steady state, please? Any question, guys? Are we good? Babuza? Can we continue, guys? Hey, guys, can you hear me?
So, Iceman, Mr. Ice,
Hmm. Yes, Abubakar. Talk, my brother.
I'm okay, man. Are you recording the class?
Yeah. This class has been recording. It's been an
Yes, you can
hour
continue, Ice.
and 15 minutes. This class might even be. That was your only question, Mr. Abubakar.
I'm saying, are you recording the class?
I've showed you. Do you see the time that is counting here?
So, man,
It's
if you
been
can send the link today, man,
an
then
hour
we
and
practice.
16 minutes. So this video I'll upload it just after the class. It's recording. So Mira, my question is about that was the only one, right?
Yeah.
Okay. Okay, guys. Let's move to the steady state. To the state. Develop the state space model. Guys, this state space model, I'm pretty sure they will give you a project. I'm not sure if it's on vibration, but I believe it's on this one. The reason why you guys usually develop in state space model, it is simply to come out with a simple expression that you can put on MATLAB to do your simulation. But it cannot be always MATLAB as a software that uses simulation, but MATLAB is one of them that our lecturer want us to use. So steady state model. Ooh, okay. Here we go, Mr. Ubaka. How do we solve the steady state model? There's actually one formula to use. Everything should be in terms of z dot. Yeah, I like calling it z to avoid confusion. Some people put x dot and not there, but I like calling z in terms of z dot. Az, let's say, plus bu. I think there's another formula, but take this one first. Let's do this one. So what does it mean, Mr. Obaka? Basically, what we are doing, Mr. Obaka, we want to we want to simplify this equation in such a way that, wait, can you guys see my screen, guys? Hello?